Okay, pulse motor build off is over. Congratulations to the 3 winners. A big thank you to Zero Fossil Fuels for taking the time to judge first place in the competition. It was done very professionally, as all his work is. Pop on over to his website and have a look what he does. Does some very, very good stuff over there. Another big thank you to Kyle Carrington and Peter for donating first, second and third prizes. Absolutely awesome, guys. And also a big thank you to the 2 girls for judging second and third, that being my wife and of course Russ's wife, who also himself needs a big thank you for all the time he spent on videos and keeping everyone up to date on how the build off was going. readings.Com. Go and check out his work. Very, very fancy stuff. And very big into Stan Meyer's HHO setup, so a worthwhile look over there as well. Okay, that being said, what we're going to be looking at today is multimeters measuring current in pulse systems and voltage also. They don't like it, plain and simple. And the more current you draw through your system, the more of a hissy fit your multimeter will have. So what we're going to do first, and I'll run through what I've got here. I stripped back a couple of old meter leads so I could hook the probe to the scope up to them, as you can see, and this is going to show us actually what's happening across the shunt inside the meter and what your meter is trying to read. Most meters will say, oh yeah, look, we can handle a pulse DC, but they really don't like it. So we need to get rid of that, and we're going to use a couple of decent sized caps to do that. The more current your system draws, the bigger the caps will have to be in capacity. So we'll fire the system up. We are going to use this system, and we've been using it and experimenting on it the last few days, as Mag just happened to post a video on something very interesting that can be achieved with some systems, and I've jumped on it and started experimenting with it because it held great interest to me, and as it turns out, a lot of other people. The more we jump into it, the more mystery we get from it. But with this setup, we're going to explain a few things and maybe answer some questions. But first off, we've got to get rid of the pulses. So we start our system up. We are drawing 30.7 milliamps at the moment, as we are using the milliamp side of the meter set on the 200 milliamp scale, as the 20 of course would be too small. So about 30.7, 30.8. Here we're coming out of the battery, we're hooked on the negative rail of the caps. We're coming straight off of that going to the emitter. As you can see, nothing is on the positive rail. So we come from our battery through our meter and out of our meter, excuse me, trying to get over this flu, and into our system. What we have across the meter at the moment is that, and that is what the meter is trying to get a reading from. Now, although that looks bad, it's not really that bad. I thought it would have been a little worse, but it's not, and that's due to the fact we're only drawing a very low current, so the shunt in the meter across the milliamp scale is doing a pretty good job at handling it. We are set at 20 microseconds in the time divide, and we are set at 50 millivolts on the volts divide. So the actual spike across the meter that the meter can't keep up with is only about 170 to 180 millivolts, which is not too bad, but still it will throw the accuracy out a little bit. And like I said, the more current you're drawing, the worse that will get. If I turn this up, you can see indeed it does get worse. But we will drop it back down to our 30, as close as we can get it. Close enough. We're only going to go to the third decimal point anyway in these measurements. Okay, so our meter's saying yes, your system's drawing 30 milliamps at our battery voltage. Now this battery voltage, we're going to pretend we don't know, because that's going to come into play a little later on. Okay, so let's get rid of these pulses. How are we going to do that? We're going to use two big caps. Now capacitors, the internal resistance inside a capacitor, unlike a battery, is very high. However, the series resistance in a capacitor is very low, in the order of 1 ohm or lower. So what we will do later on is add this 1 ohm to this 100 ohm resistance. And for those of you who know what's going on, you've probably started to work this out already. But anyway, we're going to get rid of that mess, and we're going to see how well the caps do that. So we'll disconnect it from here. A word of advice: two big caps empty, your meter's on milliamp scale, you go plug it onto those two big empty caps, you're going to pop the fuse in your meter, because the caps will want to draw a lot of current to fill up. So first, fill your caps up to the battery voltage, otherwise you will be changing fuses in your meter. We can then safely hook the meter up. We can now go from the caps. I am trying to keep everything in view, but watching what I'm doing and watching through the camera at the same time becomes a little tricky. We'll put it back on the system. As you can see, the current draw has only gone up slightly. So like I said, that meter was doing a pretty good job at smoothing out the pulses in that system that's drawing that low current. There is now the line across the meter, and as you can see, it's totally smooth, no more pulses. So we'll run through that again. I'll just connect it from the caps, take it off, plug it straight from the meter onto the machine. Our meter is seeing pulses. Disconnect our meter, put it back on the caps, and draw the current from the caps instead, and no more pulses. So now we are getting a very accurate reading, because it is running a smooth current through the meter instead of a pulsed current. So okay, we've got rid of that problem. So here comes the next problem, and this is where I believe we go wrong. Now a lot of you would have heard of a man by the name of John Bedini, who claims that some of his machines can put out more energy than what they consume. You also heard a lot of people taking a 12 volt battery and charging a flat 12 volt battery up to 16 volts while only losing about half a volt in a battery of the same size. And along with many others. I myself found that very hard to believe, and until now, the last week or so playing with this circuit, did not believe in a device that could put out more energy than what it consumes. But here's what I believe is wrong with our measurements and how we take them. What we're going to do now is turn off the system, and we're going to take our power from the other side of our 100 ohm resistor. We'll start our system back up. As you can see, still totally smooth. Of course, our current draw has dropped down. It is slowly going up because it's filling the caps back up. And it's gone down because we now have an extra 100 ohms resistance in the system. So we will turn it back up to our 30. Okay, close enough. So we want to find out the battery voltage. Now, how do we do that? Well, we can use Ohm's law to find out the voltage of a battery in a series circuit. All we have to do is times our amps by our resistance. So we know our amps are 30 milliamps. And we know our resistance is our 100 ohms here, and we're going to go high. It would be lower, but we will say 1 ohm for our caps. So 101 ohms on our resistance. So now we can get our battery voltage, and that would be 3.03 volts according to Ohm's law. Okay. Now we can grab our other meter, and we're going to measure the battery voltage. Okay, well, this meter's saying the battery is 12.4, and Ohm's law is saying the battery is 3.03. So what's happening there? Now, that is just a little something I wanted to throw in, and the reason being is automatically we keep on multiplying our battery voltage by our current draw and assuming that that's what the system is drawing. And if we did that, we would think that our current draw is 372 watts. But if we use Ohm's law, it says our current draw is 0.090 watts. So there's a very big difference between those two current consumptions of the system. So that's where it comes in a little tricky. We may have a potential voltage of 12.4 volts, but the system is only consuming 3.3 volts at our now 31.9 milliamps. So Makes things very interesting when measuring currents in systems, and one of the reasons I believe that this measurement is right instead of this one up here is because if we had that much current going through a little half-watt resistor, it would be slowly getting warmer, but it is not. It is stone cold, as cold as the night is out here. So I would like everyone's thoughts on that. Have we been measuring the input of our machines wrong? And is our friend John Bedini indeed right? I am starting to lean towards yes. It is very possible. So there you have it. 101 ohms, 34 milliamps. Ohm's law says the voltage of the battery is 3.03 volts. Our meter says the battery voltage is 12.40 volts. So which is it, guys? Let us know. Have a great night and cheers from the Tin Men.